Welcome back to the Deep Dive, powered by the Generative AI Futures podcast.
Great to be here. And yeah, today we are definitely strapping in for the ultimate technical dive.
Absolutely. Forget the high-level summaries of open source LLMs folks might be used to.
Right? We're taking a deep submersible ride, straight into the engine room of this whole local AI revolution.
That's it, exactly.
Okay.
Our mission today, really, is a comprehensive, pretty intensely technical report on the architecture of Llama.cpp.
A project that's gotten super famous.
It has. It's known for democratizing access to large language models, but how it pulls that off, well, that's pure low-level engineering genius. We're going deep into the C and C++ internals, the specific highly optimized choices that let these, multi-billion parameter models run efficiently on consumer-grade hardware. This stuff's sitting right on your desk.
And focusing on that how is so key, I think, to understanding where AI deployment is heading. We're talking AI at the edge. For years, real high-performance AI meant these enormous GPU clusters in hyperscale data centers, miles away.
The cloud, basically.
Exactly. But now, thanks to the approach pioneered by projects like Whisper.cpp and Georgy Gerganov's Llama.cpp, there's this huge growing interest in efficient transformer inference that happens right there on device.
And you see the results everywhere, don't you? Developers showing off real-time voice recognition on a tiny Raspberry Pi.
Or running a 70 billion parameter model on a MacBook Pro, which would have sounded impossible just a few years ago.
It really is about portability and performance without being tethered to the cloud.
And the core philosophy, the source material lays it out pretty explicitly. It's non-negotiable. Simplicity, compactness, and just relentless performance optimization, but focused only on inference.
Not training, not research flexibility.
No, none of that. They deliberately sidestepped the complexity of traditional AI frameworks like PyTorch or TensorFlow to build something that's essentially an inference kernel.
It's a kernel, like an operating system kernel.
Kind of like that, yeah. A lean, mean machine designed purely for deployment efficiency above everything else.
Okay, so let's unpack this blueprint. We've sort of identified 3 key architectural blocks that make this magic happen, and we should go into each one.
Sounds good.
First, there's GGML, which is the foundational CC++ tensor library doing all the math.
The engine itself.
Second, GGUF, that universal file format that bundles up the model weights and the config.
The container.
And third, the highly specialized acceleration backends. We'll look specifically at Metal for Apple Silicon and CUDA for NVIDIA, because they leverage really specific hardware features.
Got it. GGML, GGUF, and the backends. Let's do it.
Okay, let's start at the beginning then. GGML, Georgy Gerganov's original library. This really is the cornerstone, isn't it?
Absolutely fundamental. And it's crucial to understand it wasn't built as just, another version of PyTorch or TensorFlow.
Not just an incremental update.
No, the sources frame it more like a fundamental rethinking.
Yeah.
Almost an antithesis to the flexibility-first approach you see in the big Python frameworks.
So it's like a deliberate philosophical choice.
Totally. Mainstream AI frameworks, they're optimized for research, right? They need to be flexible, handle dynamic graphs, let people experiment quickly.
Which sounds good.
It is good
Yeah.
for research, but it comes at a cost. Significant runtime overhead, huge dependencies, massive library sizes.
All right.
GGML flips that entirely. It's purpose-built for deployment and inference only, and its design follows these really strict principles: minimalism, portability, and resource efficiency.
Okay, minimalism. How minimal are we actually talking here? The source material mentions something pretty striking.
Yeah, the core GGML library is self-contained in, less than 5 CC++ files.
Less than 5 files, seriously.
Seriously. And that has huge implications for building and deploying it. You don't need a complex build system like CMake or Bazel. You don't need huge external libraries.
Just a C compiler.
Pretty much. Just GCC or Clang. And by sticking to older, super compatible standards like C99 and C++ +11 or 17, they make sure it runs almost anywhere. Maximum reach across basically every system configuration you can think of.
And the result of that simplicity.
Yeah.
The compiled binary size.
Often less than a single megabyte.
Less than a mega. Compare that to, what, hundreds of megs for a basic Python environment plus PyTorch.
Easily. Hundreds. And that small footprint is the key difference, right? It's what lets you run a powerful LLM on a regular consumer device instead of needing a server farm.
It allows GGML to be embedded everywhere.
Exactly. By 86, 64 machines, ARM chips, Apple Silicon, even low-power embedded systems running Linux or Android, it completely cuts out that massive Python dependency tree.
Okay, so minimalism, portability.
Mm-hmm.
This focus on resource efficiency also leads to something called the zero allocation principle.
Ah, yes, this one's critical.
It sounds important, but what does it actually mean in practice? Zero memory allocations during runtime. What does that buy you?
It buys you predictability and speed. It avoids two huge system headaches: latency spikes and memory fragmentation.
Okay, how?
Well, think about normal programs. They're constantly asking the operating system for memory, using functions like malloc and C, and then giving it back with free.
Right.
Every one of those calls has overhead. And when you're doing a complex tensor math, you might be requesting and releasing thousands of little memory buffers really, really quickly. That overhead adds up, it becomes unpredictable, and it can fragment your available memory.
Making future allocations slower.
Exactly. GGML just bypasses all of that.
So how does it manage memory then, if it's not asking the OS?
It puts the responsibility on the user up front. Before anything runs, when the model initializes, the user has to figure out the maximum memory they'll need for everything.
Everything, like weights, activations?
Weights, activations, the computational graph metadata, any temporary buffers, all of it. You calculate that total size, and then you allocate one single, massive, contiguous block of memory. That's your arena.
Managed by the ggml context object.
Precisely. And once inference starts, ggml only ever carves out pieces from that fixed, pre-allocated block. It never goes back to the OS to ask for more.
Wow. So once the engine is running, the OS basically doesn't hear from it again regarding memory.
Correct. It's just reading and writing within its own little memory sandbox.
Which gives you that super low latency, predictable performance because you've cut out the OS memory manager lottery.
That's the core idea. It's a trade-off, a big one. You absolutely sacrifice the ease and flexibility of Python's dynamic memory handling.
But you gain raw, guaranteed deployment speed.
Exactly.
Okay, this quest for raw speed doesn't stop there, does it? It goes right down to the CPU instructions themselves with SIMD optimization.
Single instruction, multiple data. Yep.
Now, most people know C and C++ are fast. But why is ggml's specific use of these SIMD intrinsics such a big deal for performance?
Because when you're writing pure C or C++, you get direct access to the bare metal, to the hardware. Traditional frameworks often use more generalized code, kernels that work okay everywhere but aren't perfectly optimized for any one place.
Sacrificing specificity for breadth.
Right. But ggml, because it only cares about inference operations, things like matrix multiplication, convolutions, the stuff LLMs do constantly, it can use hand-tuned code that maps almost directly to the CPU's specific instruction set.
Okay, let's make that concrete. The source material used the example of a vector dot product.
Perfect example. A simple, standard C loop for a dot product. It processes one floating point number at a time per instruction cycle. That's a scalar operation.
One by one. Slow.
Relatively slow, yeah. ggml throws that loop out and replaces it with SIMD intrinsics. So if you're on a modern Intel or AMD processor by 86, that means using AVX2.
And AVX2 lets the CPU process
8 single precision floating point values simultaneously in one instruction.
8 at once, and on ARM, like Apple Silicon or mobile chips.
On ARM, it uses neon intrinsics. Depending on the specific instruction and data type, that often means processing 4 or maybe even 8 floats simultaneously too.
So you're looking at like an instant 4x to 8x performance jump on these core mathematical operations just from using the right CPU instructions.
Pretty much, yeah. It's a massive difference.
But hang on. If ggml is using AVX2 on by86 and Neon on ARM, and those are totally different platform-specific instruction sets, doesn't that break the whole portability promise we just talked about?
Ah, that's a really sharp question. It seems like a contradiction, right? How can it be portable and use hyper-specific instructions?
Yeah, how do they square that circle?
Through careful abstraction and, frankly, a lot of hard work. The core ggml computation graph itself, the sequence of operations, that's hardware agnostic. It just says, do a matrix multiply here.
Okay.
But when it's time to actually execute that matrix multiply, the library looks at the hardware it's running on. The GGML developers have written multiple versions of the critical performance-sensitive functions like quantized matrix vector multiplication.
So there's an AVX2 version, a Neon-on version.
An AVX version, maybe a version for older SSC instructions, and even a plain C fallback version for CPUs without any fancy CMMD capabilities.
Got it. So the library detects the CPU features at runtime, or maybe the compiler selects the right path when building.
Exactly. It uses conditional compilation and runtime checks. So the high-level logic stays portable, but the low-level execution path gets automatically routed to the fastest available implementation for whatever specific hardware you're running on.
That's a pretty sophisticated way to get the best of both worlds. Portability and specialized speed.
It's a clever engineering compromise. It ensures you get the maximum possible performance out of each target platform without having to maintain completely separate code bases.
Okay, so building on that philosophy of minimalism and performance, let's transition now to the actual concrete stuff. The low-level architecture you can basically see laid out in the ggml.h header file. This is how the engine is actually put together in memory. Right, the nuts and bolts. And we start with that foundational memory manager we already touched on, the ggml context. This is the memory arena.
Absolutely central. When you initialize it using ggml params, this context structure holds that single big block of pre-allocated memory we discussed.
The sandbox.
The sandbox, exactly. It's responsible for holding everything. The metadata for every single tensor, the definitions for the computation graphs, and if you're just running on the CPU, the actual tensor data itself often lives there too.
And its main job is providing that super efficient internal allocator that, crucially, never talks to the OS's malloc after initialization.
Correct, ensuring that consistent low latency performance.
Okay, so context manages the memory. Next up is the Gmail tensor. And this is where the C structure gets really interesting. You said it's like a smart node.
Yeah, I think that's a good way to put it. It's not just a passive chunk of data like a NumPy array might be. It's both a container for data and an active node within a computational network.
How so? What's inside the struct Gmail tensor?
Well, you have the stuff you'd expect. A type field, which tells you the data type. Is it float 32, float 16, or one of the many quantized integer types?
Like Q4KM or IQ2XXS we'll get to later.
Exactly. Then you have endims for the number of dimensions, ni, which holds the shape or extent in each dimension, and nb, which stores the byte, strides how many bytes to jump in memory to get to the next element along each dimension. Standard tensor stuff.
Okay, that sounds like the physical layout. What makes it smart?
It's the structural information baked into the tensor struct itself. There's an op field. This identifies the specific operation like matrix multiply or an activation function like RayLU that created this tensor.
Oh, so it knows how it was born.
Precisely. And even more importantly, it has SARC0 and SARI1 fields.
Yeah.
These are direct pointers back to the input tensors that were used in that operation.
Wait a minute. So if I have the final output tensor, see the logins prediction.
Yeah.
I can look at its OT to see what calculation made it, and then I can follow its SARO0 and SARO1 pointers to find its inputs. And then I can look at their ops and their sources and keep going backward.
You got it. You can trace the entire chain of computations, the whole history, just by following these pointers back from the final output.
So the entire execution plan, the directed acyclic graph of operations, is implicitly encoded right there within the metadata of the tensors themselves.
Exactly. It's an incredibly elegant and compact way to define the computation. You don't need some separate, potentially massive graph object floating around while you're just defining the model logic. The graph structure emerges directly from the relationships between the tensors.
That is clever. Okay, so the tensors hold the implicit history, but you need something concrete to actually execute. That brings us to the third core structure, the GGL graph.
Right. If the tensor links provide the implicit blueprint, the GGML graph is the explicit ordered step-by-step instruction list for execution.
So what is a GML graph?
Fundamentally, it's quite simple. It's basically just an array or list containing pointers to GL-tensor objects, but crucially, they're in a specific order.
The execution order.
The exact sequence of operations that need to be performed, node by node, to compute the final result. Tells the engine, compute this tensor first, then this one using the result of the first, then this one, and so on.
And how is this graph generated? You don't build it manually, right?
Oh, definitely not. It's generated automatically. You tell GGML which tensor you want to compute, usually the final output tensor, and you call a function like ggmbuildForwardExpand. It traverses backward from your target tensor, following those SURF-EOA ERC1 pointers we talked about.
Visiting all the necessary precursor tensors.
And builds up that ordered list of tensors that represents the forward pass computation needed to get your result.
And the beauty you mentioned is that this resulting list, this GGMLA graph, is still hardware agnostic at this point. It's just a sequence of steps.
Exactly. It doesn't know or care how those steps will be executed yet. It just defines the work.
Which perfectly sets up the next stage. Handing that graph off to a specialized hardware backend like CPU, Metal, or CUDA, which then iterates through the list and calls the right optimized kernel for each tensor's op.
That's the core loop. Define logic with tensor's trace lineage to build the graph, hand graph to backend, backend executes optimized kernels.
Okay, but you mentioned this gets more complex with backends. The simple CPU flow keeps everything tidy in the main GNO context. But the backend abstraction flow, needed for GPUs, has to deal with separate memory spaces.
Right. This is where things get significantly more intricate because now your data isn't all in one place. Some is in system RAM, some is in the GPU's VRAM.
So let's trace that specific low-level flow. Say we want to use the CUA backend for an NVIDIA GPU. What are the steps focusing on that memory separation?
Okay, step by step. First, you initialize the specific backend. You'd call something like ggm backend cuDNet 0 to set up communication with the first GPU.
Step 1, talk to the GPU.
Step 2, initialize the main ggml context just like before, but with a critical difference. You set the noalloc parameter in ggminute params to true.
Noalloc true, what does that do?
It tells the context, okay. You're still in charge of managing the metadata for all the tensors, their shapes, types, names, the graph structure pointers, SRREs, RAOC1. But do not allocate any space for the actual tensor data, like the weights, in the main system RAM block you manage.
So the context holds the blueprint, the plan, but not the actual heavy materials like the weights. Those will live elsewhere.
Precisely. The context manages the metadata pointers, but the data buffer itself will be on the GPU.
Okay.
Step 3.
Step 3 is creating all that tensor metadata within the context. You define all the tensors your model needs, their names, dimensions, types, operations, but again, without allocating their data buffers in the context's memory.
Just creating the empty shells, metadata-wise.
Right. Step 4 is where you actually allocate the memory on the device. This involves creating a GL backend buffered. Think of this as reserving a big chunk of the GPU's VRAM.
Okay, GPU memory allocated. Step 5. Now you need to get the model weights, which are probably loaded from the GGUF file, into system RAM initially onto the GPU. You use a function like ggml backend tensor set to copy that weight data from RAM into the backend buffer you just created on the GPU.
Weights are now on the GPU. We're getting closer.
We are. So the static weights are handled, but what about all the temporary tensors, the intermediate activations that get created and destroyed during the forward pass?
Right. Those can't live in the main CPU context if we want speed. Do they go on the backend buffer too?
Not quite directly. This is where another advanced but crucial component comes in, the GGL Galliker. It stands for Graph Allocator.
Graph allocator, Galliker.
When you build the computation graph, ggml graph, the system analyzes it to figure out the lifetimes of all those temporary intermediate tensors. The ggml Galliker then takes charge of managing memory for these specifically on the device. Its job is to allocate space for them within the GPU's memory, often from that same back-end buffer but managed smartly, just before they're needed, and free it up as soon as they're no longer required by subsequent operations in the graph.
So it's like a specialized memory manager just for the temporary stuff, running entirely on the GPU side.
Exactly. It's designed to minimize memory fragmentation on the GPU and, crucially, to avoid having to constantly copy these temporary activation tensors back and forth between the CPU and GPU, which would kill performance. It keeps the intermediate computations flowing smoothly within the fast GPU memory.
That makes sense. Efficiently managing those temporaries on device is vital. Okay, so graph allocator is set up.
Yep. Then you actually execute the graph on the device using GML backend graph compute. This tells the backend, CUDA in this case, to run through the ggml graph node list using the weights and temporary buffers allocated on the GPU.
The GPU does its work. Are we done?
Almost. One final necessary step for this backend flow. You need the result. The final output of the model, usually the logits vector, is now sitting in GPU memory. But the CPU needs it to do the token sampling. Picking the next word. So you need GML back intenserted.
Copy it back.
Copy it back. This function copies the final result tensor data from the GPU's backend buffer back into regular system RAM so the CPU can access it and decide what token comes next.
Okay, that whole detailed flow in it backend, context with noalloc, create metadata, allocate device buffer, copy weights over, use Galliker for temps, compute, copy result back, really highlights the separation and coordination needed for GPU offload.
It does. And understanding that separation is key to understanding the final piece here, the GGL backend SHID, the scheduler.
Like the scheduler. This manages hybrid execution using that Sheen-Polaris argument.
Exactly. The scheduler is the orchestrator that makes sense of this complexity in a flexible way. Let's say you use Angle 30 to offload the first 30 layers of your model to the GPU.
Wow.
The scheduler builds the graph. But maybe layer 28 uses some I don't know, really obscure operation or an old quantization format that the GPU backend just doesn't have an optimized kernel for.
It hits a roadblock on the GPU path.
Right. The scheduler's smart enough to detect this. It sees that the GPU backend can't handle the op for the tensor at layer 28. So instead of crashing, it automatically reroutes just that specific operation back to the CPU. The CPU computes that one tensor. The result is maybe copied back to the GPU if needed for layer 29, and the rest of the computation continues on the GPU.
Wow, so it can dynamically split the work between CPU and GPU, operation by operation if needed, based on what each backend supports.
Yes. It ensures the whole process keeps running and makes the best possible use of all the available hardware, even if it means doing this intricate dance between CPU and GPU memory spaces mid-computation. It's what lets you run part of a huge model on a smaller GPU, maximizing your hardware investment.
Okay, that was a deep dive into the engine itself, ggml. Now let's talk about how the actual model, the weights, the configuration gets packaged and stored. This brings us to GGUF.
The ggml universal file format, yep.
And this wasn't the first format, right? GGUF was an evolution.
It was a really necessary evolution, a major step up in terms of engineering maturity. Its predecessors, like the format often called GGJT, had a big problem. They relied on fixed C-style structs in the file header to store the model's hyperparameters, things like the number of layers, the embedding dimension, context length, etc.
Fixed C-structs. I can see where this is going. What happens if the model architecture changes?
Exactly. If the original model authors decided to add a new hyperparameter, or even just reorder the existing ones in the struct, any older program trying to load that new model file would likely crash or read garbage data, because its definition of the struct didn't match the file anymore.
Classic software fragility. Breaking compatibility. What people sometimes call dependency hell.
Precisely. It was brittle. GGUF completely solved this by moving away from fixed structs to a flexible key-value metadata section.
Key-value pairs, like a dictionary or a map.
Sort of, yeah. Stored serially in the file. Instead of fixed fields, the metadata section contains a list of entries. Each entry has a string key, like llama.contextLength or general.architecture, and then the corresponding value, an integer, a float, a boolean, a string, even an array.
How does that help with compatibility?
Because now, if a new version of llama.cpp adds a new parameter, say llama.rope scaling type, it just adds a new key value pair to the metadata. An older program loading that file will simply encounter this key it doesn't recognize.
And just ignore it.
It reads the keys it knows, skips the ones it doesn't. This makes the format incredibly robust and forwards compatible. Newer models can add features without breaking older loaders. It just works.
That's a huge improvement for stability. And the usability for the end user seems transformed too. The sources emphasize the self-contained nature.
Oh, massively. A single .guf file bundles everything you need to run the model. All the weights, often quantized, the complete model configuration via that key value metadata, and even the entire tokenizer vocabulary needed to convert text to tokens and back.
So no more hunting for separate config files or tokenizer files that have to perfectly match the weight file.
Nope. It's the principle of the atomic artifact. You download one single file, and you have a guaranteed runnable LLM. It eliminates so many potential user errors, configuration mismatches, and dependency issues. It's clean.
Okay, let's get into the weeds a bit. The byte-level structure of a GGUF file. It's a binary format, uses little endian byte order, and it's organized into four main parts, sequentially. What's first?
First up is the header. It's small and has a fixed size.
What's in the header?
Just the essentials to get started. It contains the magic number. It's always 0 by 47475546 in hex, which is GGUF and ASCII characters. This is how loaders instantly verify they're actually looking at a GGUF file.
Like a file signature.
Exactly. Then it has the GGUF format, version number, like version 3, etc., the total count of tensors that are described later in the file, and the total count of key value pairs that are in the metadata section immediately following the header.
Okay, so header gives the basic counts. Part 2 is that flexible metadata section we just discussed.
Right. This is where all the configuration lives. It's just that sequence of key value pairs. Each key is stored as a length prefix string, following conventions like general.name or llama.attention.headcount.
And the values. How does it know if a value is a number or text?
Each value starts with an enumerated type code, a small integer that tells the loader what data type comes next. Is it a 32-bit unsigned integer, a 32-bit float, a boolean? a length prefix string, maybe even an array of one of those types. This enum structure is what makes it so extensible. You can add new value types in future GGUF versions if needed.
Very flexible. Okay, header, metadata. Part 3 is the tensor info section.
Yep. Think of this section as the table of contents or the index for all the actual model weights, which come later. It's essentially an array where each element in the array describes one tensor in the model.
And what information does it store for each tensor?
Several key things. A unique name for the tensor, usually a string like blk.0.atnnorm.weight or output.weight. It's shaped the number of dimensions and the size of each dimension. Its type, this is crucial, it specifies the ggml data type, telling the loader if it's F32, F16, or importantly, which specific quantization scheme like Q4KM, IQ3S, etc. is used for this tensor's data.
Okay, name, shape, type.
What else? The most critical piece of info here is the offset. This is a number, usually a 64-bit integer, that indicates the exact byte position within the final data block where this specific tensor's weight data actually begins. It's a pointer into the big data section at the end.
Got it. It's the map telling you where each piece of treasure, the weights, is buried in the final part of the file.
Good analogy. And that brings us to the fourth and final part, the padding and tensor data.
Now, padding often sounds like wasted space. Why is there padding before the actual multi-gigabyte block of tensor weight data? Why is that important?
The padding isn't wasted space at all. It's actually a critical performance optimization directly related to how operating systems handle files. The metadata section usually specifies a required alignment, often using a key like general dot alignment, maybe set to 32 or 64 bytes. The padding exists purely to ensure that the start of the main tensor data block falls exactly on a memory address that is a multiple of this alignment value.
Okay, alignment. Why does the OS care if the data starts at byte 10,000 or byte 10,024?
Because of memory mapping, or mmap. This is a system call that Llama.cpp uses heavily for loading models efficiently.
We hear map mentioned a lot. Can you break down why it's such a huge win for loading these enormous model files?
Sure. So imagine you have a model file that's, say, 15 gigabytes or maybe 30 gigabytes for a big one. If you tried to load that using traditional file reading, like reading the whole thing into a buffer in RAM, you'd need 15 or 30 gigs of free RAM just to start, and it would take ages to read from disk.
Your system would probably choke.
Probably. mmap avoids this. It asks the operating system to map the entire file into the program's virtual address space, but without actually reading the data into physical RAM yet. It's like telling the OS, pretend this giant file is already in memory at this address range.
So it's virtual loading, almost instant.
The mapping itself is almost instant, yes. The clever part is what happens next. When your program actually tries to access a specific part of that mapped memory, say, the weights for layer 5 the CPU triggers a page fault. The OS catches this fault, sees that the requested data isn't actually in physical RAM yet, goes and reads just that specific page, usually 4 KB or 16 KB, from the file on disk into RAM, and then lets the program continue as if the data had been there all along.
Lazy loading. The OS loads chunks of the file from disk into RAM only when they're actually needed.
Exactly, on demand. This makes model loading feel instantaneous and drastically reduces the initial physical RAM footprint because only the parts of the model you're actively using need to be resident in RAM at any given moment.
Okay, so how does the alignment padding help map?
The OS manages memory and file I/O in these fixed-size blocks called pages. Memory mapping works most efficiently when the data you want to access aligns well with these page boundaries. If your tensor data starts at some random unaligned byte offset within the file, accessing it might require the OS to load multiple pages or deal with tricky boundary conditions. By ensuring the entire tensor data block starts on an address that's nicely aligned, for example, a multiple of 32 or 64 bytes, which usually aligns well with cache lines and page structures, you make the OS's job much simpler and faster when it needs to page in parts of the model during inference.
So the padding is like paving a smooth, wide on-ramp for the OS to efficiently load data chunks via map.
That's a great way to put it. It optimizes the interaction between the file layout and the operating system's memory management, which is absolutely critical when you're dealing with files this large. All right, so GGUF gives us this fantastic, efficient container, but the real magic behind running these huge models on regular hardware comes from what's inside that container, the quantized weights. This section, quantization, is really the cornerstone of GGML's whole approach.
Right. Quantization, we know the basic idea is taking high-precision numbers, usually 16-bit or 32-bit floating point,
Like 16 or F32, yeah.
and squishing them down into lower-precision integers, like 8-bit or 4-bit or even lower these days.
Which obviously saves a ton of memory. A 4-bit weight takes up only 1/4 the space of a 16-bit weight. But it also has a second benefit. Integer arithmetic on CPUs and GPUs can often be significantly faster than floating point math.
So it's smaller and potentially faster. How does the conversion actually work? It's not just chopping off bits, is it?
No, definitely not. It relies on what's called an affine transformation. For each original high-precision weight, let's call it the Wallerson, you want to find a corresponding low-precision integer, taller dollars. The formula is usually something like Baller approx S times WQ.
Okay, $700 scale and 0 point.
Exactly. Zeilwer's is a scaling factor, usually a float, and 0 point, usually an integer. These two parameters define the mapping. To quantize, you rearrange the formula, text round WS plus Z. To dequantize later during inference, you use the original formula, WQS times, where the dollars is your approximation of the original weight.
Got it. But the really important innovation in GGML, according to the sources, is the block-based quantization strategy.
Yes, this is absolutely key to maintaining model quality.
Why? What's wrong with just calculating one scale and one 0 point veal for an entire layer's weight tensor, which might have millions of weights?
Because the distribution of weights within a large neural network layer is almost never uniform. You'll typically have a lot of weights clustered around 0, and then some weights with very large positive or negative values, outliers.
Right.
If you try to use a single scale factor for that entire range, that scale has to be large enough to accommodate the biggest outlier. But using such a large-scale factor means you lose a lot of precision for all the smaller weights clustered near 0. You essentially squash their relative differences, and those small differences can be really important for the model's accuracy.
So one-size-fits-all doesn't work well here.
Not for high accuracy at low byte rates, no. So GGML partitions the weights within a tensor into small, independent blocks. Common block sizes are maybe 32 weights or sometimes 256.
When each block gets its own S and Z.
Exactly. Each tiny block calculates and stores its own specific scaling factor and 0 point based only on the weights within that block. This allows the quantization process to adapt locally. If one block has mostly small weights, it gets a small scale factor, preserving precision there. If another block has large outliers, its scale factor will be larger, but that only affects the quantization within that specific block.
That makes intuitive sense. It lets the mapping be much more tailored to the local characteristics of the weights.
Precisely. It dramatically reduces the overall quantization error compared to per tensor or even per channel methods, which is why GGML models maintain surprisingly high quality, often measured by perplexity, even when quantized down to very low byte rates like 4-bit or 3-bit.
Okay, let's walk through what the sources call the quantization zoo, because there isn't just one way to do 4-bit quantization in GGML, right? These schemes have evolved.
They definitely have. It's a constant area of research and improvement, always trading off between the effective bits per weight, BPW, how much space you save, and the resulting model quality.
Where did it start? With the simpler schemes.
Yeah, the early ones are now often called legacy quants, things like Q40 or Q80. Q40, for example, used a block size of 32 weights and stored one F16 scale factor for each block. Simple, gave decent compression and speed up.
But largely superseded now.
Mostly, yeah, because the accuracy drop compared to newer methods was just too significant, especially for more complex models or lower byte rates.
Then came the big breakthrough that really put GGML quantization on the map. The K-quants.
The K-quants were a major leap. Schemes like Q4KM, Q5KS, Q6K, these offered significantly better quality for a given byte rate.
What did they do differently?
Several things. They often use larger superblocks, typically 256 weights. And critically, they store the quantization parameters, the scales, and sometimes minimum values with higher precision themselves. Instead of just an F16 scale, they might use 6-bit precision for scales and minimums within the block structure.
More bits for the parameters that define the mapping.
Right. This allows for a more nuanced representation of the weight distribution within each block. A scheme like Q4KM, which achieves around 4.5 bits per weight effectively, became incredibly popular because it hit a sweet spot, really good compression and speed, with relatively little quality loss compared to F16. It's still a workhorse for general use, especially for models in the 7B to maybe 30B parameter range.
Okay, so K-quants were a big step. But the cutting edge now, according to the sources, seems to be the I-quants, importance quants.
That's right. IQ series like IQ2XXS, IQ3S, IQ4NL, these represent another fundamental shift in approach.
How are they different from K-quants? It sounds like more than just tweaking block sizes or parameter precision.
It is. I-quants incorporate the idea of weight importance. They don't treat all weights within a block equally during the quantization process.
Importance. How do you measure the importance of a weight?
It requires an extra step during the quantization process, usually called calibration. You take the original full precision model and run a small representative data set through it, maybe a few hundred examples. While doing this, you measure the sensitivity of the model's output activations to changes in each individual weight. Weights that cause large changes in activations when perturbed are deemed more important.
So you figure out which weights have the biggest influence on the model's calculations.
Exactly. This information is then compiled into an importance matrix, or IMatrix, which gets stored alongside the quantized weights in the GGUF file.
And how is this matrix used during quantization?
The quantization algorithm itself is modified. Instead of just trying to minimize the average error across all weights in a block, it becomes a weighted optimization problem. It tries much harder to minimize the quantization error specifically for those weights identified as important by the matrix, while being more tolerant of larger errors on the less important weights.
So it focuses the precision budget on the weights that matter most for preserving the model's function.
Precisely. It's a targeted approach, and the results are pretty staggering. This allows for extreme compression down to effective byte rates of 2-bit or 3-bit, while maintaining usable quality levels that would be completely impossible with older methods.
And this is how people are running things like 70 billion parameter Llama models on consumer GPUs with only 24 GB of VRAM.
That's exactly how. An IQ2XXS quantization brings a 70B model down to a size that fits in 24 GB, maybe even less. Without iQuants, trying to run a 70B model at 2 or 3 bits per weight using older schemes would result in terrible performance. The model would essentially output gibberish. Importance quantization is the key enabler for running these truly massive models locally.
This whole progression legacy, K-quants, I-quants, really highlights something you mentioned earlier, co-design. It's not just about inventing a new math trick for quantization and isolation.
Absolutely not. The engineering challenge here is huge and requires coordinating changes across the entire stack. Well, think about introducing a new scheme like IQ2XXS. First, the ggml team has to develop the core quantization algorithm itself, including that calibration step to generate the matrix. Second, the GGUF file format specification must be updated so it knows how to store not only the new quantized weight data structures, but also that accompanying matrix data. If the file format doesn't support it, you can't save the model.
Okay, algorithm and file format.
Third, and this is often the hardest part, they have to write entirely new, highly optimized compute kernels, both for CPU, using SIMD like EVX2 or Neon, and for GPU, using CDA or Metal, that specifically know how to efficiently dequantize and compute with that exact IQ2XXS format on the fly during inference.
Wow. So each new quantization scheme requires matching low-level compute kernels to be written for every supported hardware backend.
Yes. And these kernels need to be fast. Ideally, they perform the dequantization and the mathematical operation, like a dot product, in a single fused step to minimize memory access and maximize throughput. Writing a generic F16 matrix multiplication kernel is one thing. Writing a specialized CUDA kernel that efficiently handles, say, 3-bit integers with block local scales and an importance matrix lookup, all fused together. That's extremely demanding low-level systems programming.
So the format has to describe the structure, the loader has to understand it, and the compute kernels have to implement it efficiently for each hardware target. They all have to evolve together.
Exactly. It's this tight co-design between the quantization algorithms, the GGUF file format, and the hardware-specific compute kernels that makes the whole Llama.cpp ecosystem so powerful, but also why developing and maintaining it requires such deep, continuous engineering effort across multiple domains.
Okay, we've covered the engine, ggml, the container, GGUF, and the compression,
Yeah.
quantization. Now let's switch focus to the dynamic process. How Llama.cpp actually generates text, the inference pipeline itself.
Right, the actual valuation loop. And it really breaks down into two main phases, which have quite different performance characteristics.
Phase 1 is processing the initial input.
Yes, prompt processing. This is where the model takes a user's input, which could be a short question or a very long document, and computes the initial hidden states for that entire sequence in one go. Computationally, this phase is dominated by large matrix multiplications.
Because you're processing many tokens in parallel.
Exactly. If your task involves feeding the model a huge chunk of text up front, like for document summarization or retrieval augmented generation, RAG, The speed of this prompt processing phase is critical. High speed here determines your overall throughput.
Okay, once that initial prompt is digested, the model starts generating the response. That's phase 2.
That's phase 2, token generation. This is iterative. The model generates the response one token, roughly one word or subword at a time. In each step, it takes the state from the previous step, predicts the next token, appends that token to the sequence, and repeats.
And computationally, this phase looks different.
Very different. Because you're only processing one new token at a time, the dominant computation shifts from large matrix multiplies to much smaller but very frequent matrix vector multiplications. The speed of this phase dictates the interactivity of the model, how fast the words appear on the screen in a chat application.
Okay, matrix vector is faster than matrix, but you do it potentially thousands of times for a long answer. What's the key optimization here?
The absolute linchpin for making token generation fast is the KV cache.
The KV cache. We hear this term constantly with transformers. Why is it so essential? What problem does it solve?
It solves the quadratic complexity problem inherent in the self-attention mechanism. Remember, for a transformer to predict the next token, the attention mechanism needs to look back at all the preceding tokens in the sequence to understand the context.
Right, it calculates query, key, and value vectors.
Exactly. For each token, it calculates a query Q vector. And for all tokens in the context, including itself, it calculates key, K, and value V vectors. The attention score is based on how well the current token's Q matches the previous token's Ks.
Okay, so what's the problem?
The problem is, if you did this naively when generating the, say, 500th token, you would have to recompute the K and V vectors for all 499 preceding tokens all over again, just to calculate the attention scores for that 500th token. Then, for the 501st token, you'd recompute K and V for all 500 preceding tokens. The amount of computation grows quadratically with sequence length dollars.
That sounds incredibly wasteful and slow.
It's completely unsustainable for long sequences. The KV cache elegantly solves this. Since the K and V vectors for a given token, once computed, never change, we can just store them.
Cache them.
Cache them. The KV cache is typically implemented as two large, contiguous GGML tensor objects allocated in the ggml context's memory, or the backend buffer on a GTU. Let's call them K-cache and V-cache. When processing the initial prompt, as the K and V vectors are computed for each input token, they are stored sequentially in these cache tensors.
Okay, so the cache gets filled during prompt processing. What about during token generation?
During token generation, say for the 500th token, the model only needs to compute the new K and V vectors for that single 500th token. It then simply appends these new K and V vectors to the end of the K-cache and V-cache tensors. The attention mechanism can then efficiently read all the necessary K and V vectors for tokens 1 through 500 directly from the cache without recomputing anything.
Oh, so the computation for token generation step becomes roughly constant, or linear of sequence length, instead of quadratic.
Exactly. It linearizes the complexity of attention during generation, making long text generation feasible. It's arguably the single most important optimization for transformer inference speed.
But this cache must get pretty big, right? It stores K and V vectors for every token in the context window.
It does. The KV cache is often the primary consumer of memory during inference, especially for long context windows. It can easily take up several gigabytes, sometimes more than the model weights themselves, depending on the context length, model size, and batch size.
So what happens when the sequence length exceeds the allocated size of the cache? If the context window in take is, say, 4096 tokens, what happens at token 4097? Does it crash?
Good question. Llama.cpp doesn't just crash. It implements a strategy often called context shifting or rotating window. When the cache is full, i.e. you've generated CTX tokens, before computing the next token, it effectively discards the K and V vectors corresponding to the oldest tokens at the beginning of the sequence.
It drops the start of the context.
Yes. It might discard, say, the first 512 tokens worth of KV data. Then it physically shifts the remaining KV vectors forward in the cache memory to fill the gap, freeing up space at the end. Then it computes and appends the new token's KV vectors into that newly freed space.
So it maintains a rolling window of the most recent NTX tokens in the cache.
Exactly. This allows the model to continue generating indefinitely, always keeping track of the immediate past context, even if it loses information from the very beginning of a long interaction.
Clever. And to help manage that potentially huge memory footprint of the KV cache, especially for super long contexts, the cache itself can be quantized.
Yes, that's another important optimization available in Llama.cpp. Instead of storing the K and V vectors in the cache as F16, 16-bit float, you can choose to store them as F8, 8-bit float, or even INT8, 8-bit integer.
Cutting the cache memory usage potentially in half.
Or more. This can significantly increase the effective context window you can fit into a given amount of RAM or VRAM. However, there's a potential trade-off.
Ooh, what's the catch?
The catch relates to positional embeddings, specifically rotary positional embeddings, ROPE, which are commonly used in models like Llama. ROPE needs to mathematically manipulate the K and V vectors after they are retrieved from the cache but before the attention scores are computed. If the cache is storing INT8 values but the ROPE calculation expects floats, you might need to dequantize the cache values back to float first.
Adding extra computation.
Potentially, yes. And more importantly, the specialized GPU kernels that apply ROPE might be highly optimized for x16 data, but might not have an equally fast implementation for handling dequantization from INT8, followed by the ROPE math. In some cases, this could even force that part of the calculation off the GPU and back onto the slower CPU, creating an unexpected performance bottleneck.
Ah, so KV cache quantization saves memory, enabling longer context, but you need to be mindful of potential performance impacts on things like ROPE application, especially in GPUs.
It's an engineering trade-off you need to consider based on your specific needs, memory versus speed.
Okay, shifting gears slightly within the pipeline. After the model computes the final layer's output, the logits vector, which holds scores for every possible next token.
We need to actually pick one token. This is token sampling.
And it's not usually just taking the single token with the highest score, right? That's greedy sampling, which can be repetitive.
Correct. Greedy sampling, picking the argmax, often leads to dull deterministic output. Llama.cpp, particularly through the utilities in common sampling, implements a sophisticated multi-stage filtering and sampling pipeline to generate more diverse, coherent, and controllable text.
Multi-stage, how does that work?
It applies a sequence of different filtering strategies to the raw logit probabilities before the final random sampling occurs. The common filters, applied in order, might include:
Okay, what kind of filters?
first, maybe top K sampling. This simply discards all tokens except the K most probable ones. If K50, only the top 50 tokens are considered.
Limits the choices.
Then, you might apply something more nuanced, like tail-free sampling, TFSE. TFS tries to dynamically remove tokens from the tail of the probability distribution, those low probability but not impossible tokens that can sometimes lead to weird outputs. It does this based on the second derivative of the sorted probability curve.
Interesting. What else?
You could also have typical P sampling. This filters based on how surprising a token's probability is compared to the overall entropy of the distribution, aiming for tokens that are likely but not too predictable. And then there's the very popular top P nucleus sampling.
Top P, I've heard of that one.
Top P keeps the smallest set of tokens whose cumulative probability mass exceeds a certain threshold, P, e.g. P0.9. So it might keep the top 5 tokens if their combined probability is 90%, or it might keep the top 50 if the distribution is very flat. It adapts the number of choices based on the model's confidence.
And maybe min P as well.
Yes, min-P is another one, setting a minimum relative probability threshold. After all these filters narrow down the candidate tokens, a temperature scaling is often applied.
Temperature controls randomness.
Exactly. Dividing the remaining logits by a temperature value, T, before converting them to probabilities, softens the distribution. T 1.0 increases randomness, more creative, or sharpens it. T 1.0 decreases randomness, more focused. T 0 effectively becomes greedy sampling. Finally, a random choice is made from the filtered, temperature-adjusted probability distribution.
Wow, that's quite a pipeline just to pick the next word.
It gives users fine-grained control over the generation style. But Llama.cpp has one more really unique feature here: grammar-based sampling.
Grammar-based sampling, what does that do?
This is incredibly powerful for practical applications. You can provide the sampler with a formal grammar specification, typically using something that looks like Backus-Naur form, BNF. This grammar defines the allowed structure of the output.
Like enforcing the output must be valid JSON.
Exactly. Or valid SQL, or follow a specific function call format, or match some custom structure. As the sampler is about to choose the next token, it checks if that token would violate the currently active rules of the provided grammar.
And if it would violate the grammar.
It sets the probability of that rule-violating token to 0, effectively forbidding it. This forces the LLM's output to strictly conform to the specified structure. It turns a potentially rambling freeform text generator into a reliable engine for producing structured data, which is a huge win for building robust AI applications. Hashtag, tag B. The hardware backends and acceleration.
Okay, let's circle back to the hardware acceleration itself. We touched on the scheduler, GGM backend shed, and how it enables hybrid execution using the NPLR argument.
Right, that pragmatic approach. It's worth reemphasizing how important this is for accessibility.
How so?
Because it means you don't necessarily need a top-of-the-line GPU with massive VRAM to run even very large models effectively. Let's say you have a 34 billion parameter model. Running it fully in F16 might need, I don't know, maybe 70 gigabits of VRAM, which is huge.
Way beyond most consumer cards.
Right. But maybe a quantized version like Q4KM needs around 20 GB. Still a lot. But with Ankula, you can tell Llama.cpp, look, I only have a 12 GB GPU. The scheduler figures out, okay, I can fit maybe the first 15 layers of this Q4KLM model into that 12 GB GPU.
So it puts layers 0 through 15 on the fast GPU.
And then layers 16 through, say, 48, or however many the model has, automatically get scheduled to run on the CPU using those efficient SIMD kernels we talked about.
So you get GPU acceleration for the part that fits, and the rest still runs reasonably fast on the CPU.
Exactly. It intelligently partitions the graph across your available hardware, maximizing performance based on your VRAM constraints. This philosophy is key to democratizing access, letting people run bigger models than their GPU might technically hold entirely by cleverly using both the GPU and CPU together.
Makes sense. Now let's look at the specific backends. The performance of Llama.cpp on Apple Silicon Macs is often held up as a gold standard for local AI. Why is it so good? It comes down to the Apple Metal backend, right?
Yes, the Metal backend, ggml metal.mn, is crucial, but the real star is Apple's underlying hardware architecture. Unified Memory Architecture, UMA.
Unified memory. How does that differ from a typical PC with a dedicated NVIDIA or AMD graphics card?
On a traditional PC, you have system RAM connected to the CPU, and then you have separate VRAM, video RAM, sitting on the graphics card connected to the GPU. These are physically distinct memory pools.
Headed by the PCI bus.
Right. And that PCIe bus, while fast, is still a significant bottleneck. When the CPU needs the GPU to work on some data, like model weights or activations, that data has to be explicitly copied from system RAM over the PCI bus into the GPU's VRAM. Then, when the result is computed, it often has to be copied back over the PCIe bus to the CPU.
And those copies take time. Potentially a lot of time.
They can absolutely dominate the total inference time, especially for operations involving large data transfers. Apple Silicon chips, however, use UMA. The CPU and the integrated GPU cores all share access to the same physical pool of high bandwidth memory.
No separate VRAM, it's all just memory.
Pretty much. There's no dedicated VRAM distinct from system RAM. It's one unified pool. And this changes everything for the Metal backend. When Llama.cpp running on the CPU loads the model weights into memory, the Metal backend can create MTL buffer objects, Metal's representation of memory buffers, that point directly to that same memory region already occupied by the weights.
So no copying needed.
No explicit time-consuming copy operation over a PCIe bus is required. The GPU can access the data directly from the same physical memory the CPU put it in. The latency reduction is enormous. This leads to incredibly fast model loading times and near instantaneous data sharing between CPU and GPU tasks during inference.
The UMA is a fundamental hardware advantage for this kind of workload then.
It really is.
Yeah.
And combined with that, the Metal backend itself uses highly optimized kernels written in metal shading language, MSL.
And just like we saw with the CPU SIMD kernels in the quantization discussion, these Metal kernels are specialized.
Highly specialized. Again, we see that co-design principle. They have fused kernels. There isn't just one generic matrix multiplication kernel. There are specific MSL kernels hand-tuned for specific operations and specific quantization types.
So a kernel just for Q40 matrix vector multiply, and another for IQ2XXS.
Exactly. These specialized kernels perform the dequantization step, if needed, and the actual mathematical computation, like the dot product accumulation, in a single, tightly integrated operation. This maximizes the utilization of the GPU's processing units and minimizes the amount of intermediate data that needs to be read from or written back to that unified memory. It's all about efficiency at the lowest level.
Okay, UMA plus fused specialized Metal kernels explains the Apple Silicon performance story. Now let's switch to the other major backend, NVIDIA CUDA. How does it achieve high performance on traditional discrete GPUs?
The CUDA backend uses a mix of strategies. For standard high-precision operations like matrix multiplications using F16 or F32 data types, it leans heavily on NVIDIA's own highly optimized library, CUDA. Yes, it's NVIDIA's basic linear algebra subprograms library for CUDA. It contains expertly tuned routines for common matrix operations that are designed to extract near-peak performance from NVIDIA GPU hardware. Using CUDA for these standard cases is usually the fastest approach.
Makes sense to use the vendor's optimized library when possible. But what about GGML's custom quantization formats? Those K-quants and I-quants? Couplers doesn't know about those, right?
Correct. Cubeless only handles standard types like FP32, FP16, maybe INT8 in some contexts. For all of GGML's specialized formats, Q4K, Q6K, IQ2XX, etc., the Llama.cpp team has written custom CUDC plus kernels.
Just like the custom metal kernels.
Exactly. These are essential. They implement the logic to dequantize the specific GGML block format and perform the computation, Auger matrix vector multiply, efficiently, again aiming for that fused operation where dequantization and math happen together within the GPU's fast registers or shared memory, minimizing slow global VRAM access.
So coupless for standard stuff, custom CUDA kernels for the GGML special sauce, and that the whole CUDA story?
Not quite. There's one more layer of advanced optimization mentioned in the sources, which becomes particularly important for maximizing throughput on very powerful GPUs, the use of CDA graphs.
CDA graphs, what problem are they solving?
They're solving the problem of CPU launch overhead.
Launch overhead.
Yeah. Think about the token generation phase again. The forward pass through the model involves executing potentially thousands of individual CD kernels. One for each matrix multiply, each activation function, each normalization layer, etc. Each time the CPU tells the GPU launch this kernel now, there's a small but non-zero amount of overhead involved in that command submission.
Like the CPU talking to the GPU driver, setting things up.
Right, milliseconds, maybe even microseconds per launch.
Yeah.
But when you're launching thousands of these tiny kernels very rapidly, one after another, that overhead accumulates. It can lead to situations where the extremely powerful GPU ends up sitting idle for brief moments, waiting for the CPU to issue the next command. You see these as gaps in the GPU utilization timeline if you profile it.
So the CPU becomes the bottleneck, even though the GPU could go faster.
It can, especially on high-end GPUs where the kernels themselves execute incredibly quickly. CUDA graphs provide a solution. They allow the application to define the entire sequence of GPU operations for, say, one complete forward pass once, upfront.
Capture the whole sequence.
Capture the whole sequence, all the kernel launches, memory copies, synchronization points into a single graph object. Then, instead of the CPU launching thousands of individual kernels during inference, it makes just one API call to launch the entire pre-recorded graph.
One launch man executes thousands of operations on the GPU side.
Precisely. This virtually eliminates that CPU launch overhead, allowing the GPU to execute the sequence of kernels back-to-back with minimal interruption, significantly boosting throughput and reducing latency, especially for the iterative token generation phase. It's a game changer for squeezing maximum performance out of NVIDIA hardware.
That sounds incredibly powerful. But wait, the state changes with every token, right? Specifically, the KV cache grows. The pointers to the current position in the KV cache tensors change with every single generated token. Doesn't that mean the sequence of operations isn't exactly the same each time? How can a static graph handle that dynamic KV cache?
That is the crux of the implementation challenge, and where the Llama.cpp CUDA backend uses a particularly clever feature. You're right, simply recapturing the entire graph from scratch for every single token generation step would be way too slow. It would completely negate the performance benefit.
So what do?
They use a function called CUDA graph exec update. This allows them to take an existing, already captured graph execution object and efficiently patch it with updated parameters without having to rebuild the whole graph structure.
Patching the graph.
Yes. In this context, the parameters that change are primarily the pointers and offsets related to the current position in the KV cache tensors. Before executing the graph for the next token, the code uses CUDA graph executive update to quickly tell the existing graph object, okay, for this next run, use this updated pointer for the KV cache input-output. The underlying sequence of kernel executions remains the same, just the memory addresses they operate on are updated.
Wow, so they capture the graph once and then just perform these very fast, low overhead updates to tweak the memory pointers for each token step.
Exactly. This dynamic, low-overhead patching mechanism is what makes CDA graphs practical and highly effective for accelerating transformer inference, despite the constantly evolving state of the KV cache. It represents a really sophisticated level of CDA optimization within the Llama.cpp project. It's kind of the high watermark for squeezing out performance on NVIDIA GPUs.
Hashtag outro.
Wow. What an absolutely incredible deep dive. We've really gone through the engine room of Llama.cpp today.
We certainly covered a lot of ground from the core C+ up. We really did. We saw the elegance of GGML's low-level philosophy, that zero allocation, minimalist C++ engine. Then the robustness and sheer efficiency of the GGUF format, especially how it cleverly leverages OS features like map alignment for fast loading.
The container matters.
And finally, those highly targeted, hardware-specific optimizations in the acceleration backends, Metal just capitalizing beautifully on Apple's unified memory.
Eliminating that copy bottleneck.
And CUDA tackling that subtle but critical kernel launch overhead with incredibly sophisticated techniques like CUD graph patching.
It's impressive engineering across the board, and I think the overarching takeaway really connects right back to that original manifesto we started with.
Simplicity driving innovation.
Yeah, that focus.
Yeah.
By concentrating so relentlessly on creating a fast, reliable, low-level inference kernel and providing stable, clean interfaces around it, the Llama.cpp team basically enabled this whole vibrant ecosystem to flourish.
You see it everywhere now.
Exactly. The success of tools built on top of it, things like Llama, LM Studio, countless Python and other language bindings, it all validates that strategy. It proves that sometimes that hacking spirit, combined with really disciplined, deep, low-level engineering, can create production-grade infrastructure that fundamentally changes how people access and use high-performance AI.
It really has democratized things in a way that few other projects have.
Couldn't agree more.
Okay, so let's wrap this up, as always, with a final provocative thought for our listeners to chew on, something to mull over based on everything we've discussed.
All right, let's frame it around those performance trade-offs. We established pretty clearly that the inference pipeline has those two distinct phases with different bottlenecks, right?
Fast prompt processing, needing high throughput on big matrix multiplies, crucial for things like summarization or RA where the input is long.
And fast token generation, needing low latency on matrix vector multiplies and efficient KV cache handling, crucial for interactive chat. So here's the question for you, the listener. If you were building an application that was focused purely on document summarization, meaning you process a potentially very long prompt in one giant batch, but the generated summary output is relatively short.
Okay, long input, short output.
Exactly. In that specific scenario, the memory consumed by the KV cache during the short generation phase becomes much less critical compared to the sheer computational speed of processing that initial long prompt. The bottleneck shifts almost entirely to that first big matrix calculation.
Right, the KV cache size isn't the main constraint if the output is short.
So, considering that trade-off, which quantization scheme would you prioritize for maximum summarization throughput? Would you go for a generalist scheme like Q6K, which offers a good balance but maybe isn't the absolute smallest or fastest for raw matrix math? Or would you push towards a highly compressed scheme like IQ2XXS, even though it might have slightly lower precision, because maybe its specific compute kernels are incredibly fast for those large initial matrix multiplications? Or perhaps something else entirely. Think about where the precision matters most and where the compute bottleneck really lies for that specific task. What configuration maximizes the speed of that initial prompt crunch?
That's a great question. Balancing the raw compute efficiency of the kernels against the inherent precision trade-offs of the quantization, specifically for that prompt processing phase. Excellent food for thought.
Hopefully gives people something to think about.
Absolutely. Well, thank you so much for guiding us through that incredibly detailed technical landscape.
My pleasure. It was fun to dive deep.
And thank you all for joining us on the deep dive. We'll see you next time.